Hello everyone, and welcome back to another GIS for Mathematics tutorial video. And in this video I want to continue our discussion talking about the standard equation of an ellipse centered at the origin. And specifically I want to build off this equation right here, which is if the ellipse is a horizontal ellipse or it is wider than it is tall. And I want to talk about what happens when this ellipse is rotated 90 degrees and it's actually taller than it is wide. And I want to talk about what changes in the standard equation and how you can sort of look at the equation that you're given to figure out if the ellipse is wider than it is tall. So again, we're going to keep these definitions in mind. This equation down here we're going to keep in mind, and we're going to see how this changes. Okay, so let's go ahead and go over here. We now have an ellipse that is taller than it is wide, and you'll see that I've done the same thing as we did before. I've labeled the vertices, the foci, the co-vertices. And what I want to do is I want to talk about what the equation looks like. So this equation is going to look very similar. It's going to be x squared over b squared plus, let me move that plus up just a little bit, plus y squared over a squared equals 1. So you'll notice this looks extremely similar. So in fact, if I were to scroll back over, you'll see x squared over a squared plus y squared over b squared equals 1. So you'll notice that when the ellipse is vertical, that the a and the b now trade places. And just to sort of recap what we talked about before, right? The distance from the center to the vertex, this is still a, right? The distance from the center to the co-vertex, right? This is still b. And the distance from the center to the foci, this is still c. Right? So a is still the distance from the center. Oops, I'm using the wrong color. Sorry about that. Right. A is the distance from center to the vertex. But here's the key difference. Now, right, instead of the vertex being 0, or a comma 0, the vertex is now going to be 0 comma a, right? A now represents the y-axis of the vertex, right? The y-axis of the vertex. Okay. All right. B is still the distance from the center to the co-vertex. Right. This is still the distance from center to co-vertex. Right? But instead of the co-vertex being 0 comma b, now it's b comma 0, right? Because now the co-vertex is on the horizontal line. Right? So this is now the x-axis. Or sorry, the x-coordinate, I should say. Sorry, x-coordinate of co-vertex. Right, the x-coordinate of the co-vertex. And then finally we have C. Right, and again, C is this distance here, but again, because we've rotated 90 degrees, right, the foci now has the coordinates 0 comma C instead of C comma 0, 0 comma C. Right, so this is the distance from the center to the foci, but this is now again the y coordinate, right? The y coordinates of the foci. And again, we have that same relationship from before, that c squared equals a squared minus b squared. Right, so this key relationship still holds true. So at this point, hopefully you sort of realize a trend. And the trend is that the number a, right, this value a, so let's give ourselves a little bit more room, right? So for any ellipse, for any ellipse, right, a is always going to be bigger than b. Right, let me repeat that. For any ellipse, a is always going to be bigger than b. And it makes perfect sense, all right, because no matter how we rotate this ellipse, right, the distance from the origin to the vertex will always be greater than the distance from the origin to the co-vertex, right? Because think about it. If we pulled the ellipse and pulled the ellipse and pulled the ellipse until it was wider than it is tall, well, suddenly your axes would flip and this would become the vertex. This distance would become A. Hopefully that didn't break your mind too much. But the way we've defined the ellipse, with the major axis always being the one that cuts through the longest direction, means that no matter what we do, right, no matter what we do, for any ellipse, A will always be bigger than B. So the way that I always remember this is if A squared, sorry, let me erase that. So for any ellipse, A squared is always going to be greater than, or A is always going to be greater than B. All right. So if the larger number is under x squared, then the ellipse is wider than it is tall. All right, so this is horizontal. Okay, all right, so this would be x squared over a squared, right, versus y squared over a squared, right? If the larger number is under y squared, right, the ellipse is taller than it is wide, or it is a vertical ellipse. Right, and you can flip that around, right? If it's a horizontal ellipse, if it is wider than it is tall, then you're going to put the A underneath the x squared. If the ellipse is taller than it is wide, then you're going to put the a squared under the y squared. Hopefully this makes sense. This is the way that I keep it straight, right? The bigger number is always a, and you're going to put that bigger number underneath whatever direction the ellipse is wider. So if it's wider in the x, you're going to put a under x squared. If it's wider or longer in the y, you're going to put the a under the y squared. That's the way that I keep track of it if you see the ellipse. If you see the equation, or if you just given the standard equation, right, if the larger number is under the y squared, then you know the ellipse is going to be taller than it is wide. If you're given the equation and the bigger number is under x squared, then you know that it's going to be wider than it is tall. We're going to look at some examples of the standard equation, so if this doesn't immediately make sense to you, I promise you that it will. If any of this was confusing, if the way the definitions flipped a little bit don't make sense, I encourage you to go back and rewatch those parts. And as always, please reach out. Thank you.